As we saw in the last video, we can use diffraction gratings to separate light into its constituent colors through interference. That's what allows us to see certain colors and at a certain position and other colors at a different position. We can also separate light by colors through interference effects with thin films. So what happens is you think about having a layer of a film. So here's a thin film. And when we have light that comes into this film, some of it bounces off the top and some of it keeps going, right? And it gets refracted. I can show that it gets refracted a little in the material, comes back out, and then comes back out. And then these rays can then interfere as they come out at different angles. They can interfere with each other. And if they are again in step, once they bounce through, then they're going to constructively interfere. And if they're out of step, they're going to destructively interfere. And so we can set up the condition based on the thickness of the film and the wavelength in the material, right? We want this thickness for us to have constructive interference. So we can pick out that color. Then we want twice the thickness to be equal to whatever's needed to get these waves back in step, right? For the waves to get back in step. And it turns out, instead of this being one wavelength, it turns out that it can be a factor of half a wavelength. For this, half a wavelength, 3/2 of a wavelength, 5/2 of a wavelength, because when we go from an index of refraction, so if this is like air, water, soap, like a soap bubble, and air again, that when we go from an index of refraction that goes from air to like water, then we actually have a phase change. So it doesn't matter. That just well, it does matter, but you don't need to worry about that. It just means that it takes half a wavelength trip, that if this distance right here, this 2 times the thickness, is equal to half a wavelength, 3/2 of wavelengths, 5/2 of a wavelength, an odd number halves of wavelengths, then we'll get constructive interference. And for this particular setup, if they are integer numbers of wavelengths, then we'll have destructive interference. So this is what explains for like soap bubbles why you get different colors that you see. They're not very bright because it's requiring reflection off of the surfaces, and light generally goes through water, but a little bit will reflect off the surfaces. And it explains why you get different colors of light, because the thickness of film is going to vary, right? The soap that helps make this soap bubble that has air inside it is thicker and thinner at different places, so you get different colors coming out. And soap bubbles are not the only place that this happens. You can see it in like the iridescent wings that you see of many animals. Beetles, certain beetles are shiny, and butterfly wings. All of those are thin film effects where the light is coming and bounces off the two surfaces and then comes back and constructively interferes. So this is actually the wavelength in the second material. So it's often labeled as N2 or lambda 2. Whoops. And where we can say that the wavelength in, if we remember, for waves, we have that the speed of wave is equal to the frequency times the wavelength. But if you're in a material, right, then we don't have the speed of light anymore. We have speed is equal to the times the wavelength in the material. The frequency is the same in both instances. So if we have air basically, or a vacuum, where we say the index of refraction is 1, and then we have our water, for example, where our speed is a little less, The frequency is the same, because remember, the frequency, if you remember back to the simulation, is driven by the oscillation that creates it, or in the case of lots of colors of light, depends on the energy level as the electron transitions and puts out a light, but somehow we get this color, and that's determined by the frequency. So the wavelength changes when the speed changes. So if the speed gets smaller, then the wavelength is obviously going to get smaller, and it's going to get smaller by this same amount, right? So if our V is C over N, then it's frequency times the wavelength in our material. I'll call it a lambda sub N. In air or in a vacuum, we would have the wavelength in air or vacuum would just be C over V. In our material, this lambda sub N is C over V 1 over N, or if we can replace that, that would be our lambda in the air over the index of refraction. So that would be our new value. Sometimes you'll see that this constructive interference condition, that 2t is equal to, say, lambda in the material, in our N2 over 2. Sometimes you'll see it like this, 2t is equal to whatever the wavelength is in air or a vacuum over N, the index of refraction, times 2. So that takes care of sort of it switching materials. So if you know the wavelength in air and the thickness, then you can figure out which ones are going to constructively interfere depending on the thickness of the material. We can apply this just to see what this looks like and get a sense for what's going on in a soap bubble. If we talk about a soap bubble that's, say, 100 nanometers thick, and we assume the index of refraction of the soap bubble is basically the index of refraction of the water. So we would have air, we would have our bubble, we have air inside, and then we have this thin layer of water soap, and we just approximate that with the index of refraction basically of the water. And so if we use this equation for looking for interference, again, it comes up from up here, we can ask what wavelength in air is going to be constructively, is there going to have constructive interference. So the idea is we have sunlight that hits this, comes in, well, I guess we should do the normal, sunlight that comes in like this, and then what color shows up most prevalently for that thickness, that region of thickness. So if we put this in, we just get 2 times 100 nanometers is equal to, finding the wavelength as it is in air, 2 times 1.33. And when I do this, I get 532 nanometers, which is a nice green color. So that tells you that this is associated with, usually I know the wavelengths for visible light, right, are the wavelengths given in air in a vacuum. So this 532 turns out to be a green color that gets constructively interfered. And so if we look right at that spot, if that spot is 100 nanometers thick, then coming out of that we would see primarily green shades. And then if we look at other points, we might see a more reddish or bluish hue depending. And it's not perfect, because soap bubbles aren't perfect and you're looking at different angles. So this is just sort of the first take on why we see these colors for soap bubbles.